Today, we are going to talk about chemical bonding. So our goal is that by the end of class, you'll be able to give a reason for why chemical bonds form in the first place. You'll be able to describe the two basic kinds of bonds. And then for the more in-depth one, you'll be able to tell me the difference between polar covalent bonds and non-polar covalent bonds, because there are a couple different types. So we'll jump right in, starting with a definition of what a chemical bond is. So a chemical bond is the attraction between the nuclei of the atoms and the valence electrons around those atoms that helps to attract them to each other and binds them together. These bonds form because it lowers the overall potential energy for that atom. As we learned when we were studying the periodic table, there's a number of atoms on this periodic table, a large number of them, that are just not very stable on their own. And when they form a bond with another atom, it lowers their potential energy, and because nature favors lower potential energy, they are more stable than they are on their own. So it helps to stabilize them. That's why chemical bonds even begin to form in the first place. They are just atoms looking to make themselves more stable. These bonds that form happen in one of two ways. The first one is an ionic bond. So in an ionic bond, what's happening is that one atom is completely taking an electron from the other atom, and then because they do that, one of those atoms becomes positive and one becomes negative, and those resulting cation and anions are attracted to each other because they have opposite electrical charges. In a purely ionic bond, the atom completely gives up its electron. The other one completely takes ownership of it, and the first one completely gives away ownership of it. Covalent bonds are different because they result from sharing of an electron. Those electrons get shared between the atoms instead of totally being given over. In a purely covalent bond, the sharing of the ownership of that electron is equal. The electron is not more attracted to either atom. It's equal ownership. Now, you may have noticed that I have qualified a couple of my statements on here by saying the word purely, right? Purely ionic, purely covalent. So that should give you a hint that most bonds that we deal with are not purely one or purely the other, which is the case. They are not usually purely ionic or purely covalent. They are usually some combination of the two, leaning more towards one or the other. The reason that atoms form a ionic or a covalent bond is because of the difference in the electronegativity between the atoms. So if you remember back to periodic trends, electronegativity is the ability to attract an electron to yourself. So some atoms can do that very strongly, and some atoms do it very weakly. If there is a large difference in electronegativity, the bond you're going to get is going to tend to be more ionic. This makes sense. If you think about it, if you have one atom that's very electronegative and can very strongly pull an electron, and one that is not very electronegative and can't pull on it very strongly, that electron is more than likely going to be attracted to the very electronegative electron, or very electronegative atom, and therefore it's going to leave the original atom and move to that one, and you're going to have a ionic bond. If, however, the difference between the two atoms is relatively low, meaning they can both pull on the electron with about the same strength, the resulting bond will be covalent. They will share it because they can both pull on it with about the same strength. The example I gave of this earlier today was, think about a tug of war, right? If both sides can pull equally, then they get to share the rope. if one side can pull much more strongly than the other, they're going to pull that rope right out of the hands of the other group. And then they're going to totally get to keep it. Not generally how we play tug of war, but it's an analogy to help you think about things. Okay. We have a lovely diagram here in our notes coming up next that is for you to look at to help determine covalent versus ionic. Okay, so it's really more of a spectrum than it is a yes ionic, yes covalent. And this diagram helps us see that. So we're just going to take a look at it real quick. Okay, so you can see on the right side, if you're looking at that x-axis along the bottom, when we have differences that are around 3, that's where we're going to get those that are almost purely ionic. There's a big gap in how electronegative they are. And on the right, or on the left side, when they have almost no difference in their electronegativity, then you'll see that we get covalent bonds, purely covalent bonds. But you'll notice that on here we have some things that say nonpolar covalent bonds and increasing covalent bond polarity. So we have something called polarity, which happens with covalent bonds. So let's chat about that. As you can see, from 1.7 and up, we consider the bonds to be more ionic than covalent. 1.7 is about 50-50. It's like 50% ionic, 50% covalent. And as you move up from there, then that percentage obviously increases. And anything 1.7 and below is then considered to be covalent, but as you saw, not all of the covalent bonds are created equal. If your difference in electronegativity is between 0 and 0.3, so very close electronegativities, you'll wind up with a nonpolar covalent bond. This happens very frequently if the atoms are of the same element, because if you think about that, same element, same electronegativity, the difference is going to be 0. So think hydrogen bonding to hydrogen is going to produce a nonpolar covalent bond. Well, what does nonpolar mean? It means that the electrons, and therefore the charge provided by the electrons, is shared equally across the entire atom. So the electrons are going to spend the same amount of time around both atoms. They're not going to be pulled more strongly to one side than the other. And as a result, the charge on that atom is going to be distributed evenly. So you're not going to have any areas of partial charges. The same is not true for the other end of the spectrum, which is a polar covalent bond. If your difference is between 0.3 and 1.7, then you're going to wind up with a polar covalent bond. What happens is that one of these atoms is more electronegative than the other. We've established that. But it's not so much more that it completely takes the electron like an ionic bond. Instead, it just pulls a little stronger, and that electron is going to spend more time near that atom. So what results is that the density of electrons is greater around one atom than the other, and therefore that atom has more negative charge than the other. So you get these molecules where one end of the molecule is slightly negative and one end of the molecule is slightly positive. And we call that polar. Like the Earth has a north and south pole. Think of it kind of like that. This has a positive pole and a negative pole. Okay. So let's just go take a look back real quick. We'll come back to this slide, but we're just going to go back quickly and look at the diagram. Okay. So over here, we have our non-polar covalent bond. So notice how those electrons are evenly spread out. They're not spending more time around one than the other, and as a result, there's no partial charge anywhere on this. But on the other one, notice how they spend more time around this atom than around this atom, and as a result, this side would gain a partially negative charge, and this side a partially positive charge. Okay? Which can be useful sometimes. Water is a polar molecule, and as a result is really good at dissolving things. So neither one is better or worse. They just have different characteristics. Okay. All right. Questions about chemical bonds?
What does that make ionic?
Ionic in and of itself, an ionic bond in and of itself would be polar because it's not even necessarily polar, it's just fully one of them is a cation and one of them is an anion. So one of them has a positive charge and one of them has a negative charge. It's not even a partial charge anymore because it's completely removed the electron to the other atom.
And then so the bigger one is the negative and then the other one's positive, the small? Like,
Not necessarily, it doesn't necessarily have to do with size, it just has to do with which one has gained the electron.
The stronger one.
Yeah, the one with the greater electronegativity should be the one that's negative. Yep. All right, that's where our notes end.